Hello everyone, this is Stacy with RheoSense. Welcome into today's webinar. First off, let me say that I hope that everyone is doing well and taking good care of themselves. And I wanted to also let you know that we really do appreciate your support, all of our customers, and then all of the other people who participate in our educational events, such as today's webinar. So thank you so much for joining us. One of the other things I wanted to mention before we get started is that the signups for today's webinar were really fantastic, not just because we had a lot of interest, but because very many people, more so than normal, filled out the comment section of the sign-up form. So people put in information on types of things they're testing, challenges they're having, questions they might have, and this was all very helpful. So thank you for that as well. And then also in the future, anytime you contact us through a web form for a webinar or any other reason, we really do appreciate and value those comments that you include. And in fact, what I thought I would do is sometimes we have a bit of a lag before people start answering or rather asking questions when we finish the formal content. So I thought I'd take some of the questions that really fit into today's topic and start answering those at the end of the webinar while people are getting ready to ask questions. And please do ask questions. Don't be shy, because if you have the question, even if you feel it's simple and straightforward, it's likely people new to the topic are also going to have that question as well. So please do ask them. They help us and everyone else. So today's topic, as you can see, is what we're calling viscosity measurement fundamentals. And after we decided on this topic, I realized that this is an extremely broad topic. As you have, as you might expect, there are entire books and week-long short courses on rheology, much of that being dedicated to viscosity measurement. So, so hopefully today we're not going to make everyone a full-fledged rheologist by the end of the hour, but hopefully you'll start to get a better understanding of the basics behind rheology and rheology measurements. And then I think in the future, what we would do is have follow-up webinars related to this topic, but sort of building upon it, adding more to it. And then I also wanted to take this moment, since we're speaking about, understanding the basics. We had intended to have a short course at our site. We're in Northern California in the Bay Area. This course was supposed to be a couple weeks ago in early March. Unfortunately, as you probably would expect, we had to postpone this. But it's basically going to, when we reschedule, which we're hoping to do in maybe mid to late summer, of course we can't commit on it now, but the idea behind it is that it would be sort of a rheology forum, an opportunity for people to come in, visit us on site, learn about rheology, meet other people interested in that subject, and then also it's a good opportunity for us to show you our instrumentation, and you can get some hands-on experience with the instrumentation as well. So if you're interested in learning things more extensively, both rheology and our instrumentation, then please check that out on our website and inquire about more information. And like I said, our hope is that we can set that up for later in the summer, but of course we have to wait for things to calm down a bit first. Okay, with all that said, let's jump into the webinar. One of the reasons, I guess I'll add a little more here. One of the reasons we wanted to do this type of webinar is that we find when we interact with a lot of our customers and then potential customers that people doing viscosity measurements now are coming from very broad backgrounds. So in the past, you would have a dedicated rheologist who focused on these types of measurements, and now things are changing. And you have people from, biologists and to engineers, biochemists, chemists, all these people with different backgrounds coming in doing the viscosity measurements. So there's a lot of misconceptions, misunderstandings, and things that they just never had the opportunity to learn because of their background. So this is one of the reasons we wanted to do this at this time, is to sort of help everyone out if it isn't your field. Okay. So, all right. So as we get started, I wanted to make a few key points that I think are important when you're getting involved in the world of rheology or viscosity specifically. So keep them in mind as we go through the webinar, and then as you move forward in general and work in this area, in this field. So one of the things I wanted to point out is that viscosity is never directly measured. It's not a directly measured property, and there's no instrumentation there that does this. And this was one of the misconceptions we recently experienced when dealing with the customer. And when I say it's not directly measured, what I mean is that it's a calculated property. So as you'll see as we go through the webinar, how we define viscosity and how this calculation process proceeds. And this is sort of where all viscosity or rheology instrumentation is on equal playing field, because it's the nature of the measurement that this calculation process exists. And although the process, which is generally multi-step, is different for each piece of instrumentation, it is still true nonetheless. So when you say viscosity measurement, it's still, it's kind of a bit of a misnomer. And the other point to make with respect to this is that when you're, using a mathematically derived formula to do the calculation, this formula was derived based on specific assumptions. And it's important to be aware of that in general, the instrumentation is almost always going to give you a number. It's almost going to actually go through this calculation process that it's been programmed to do, and it has really no way of determining if all the assumptions that went into this formula are actually being met. Now, there are some exceptions to this. So software will stop the measurement if, for example, you're in the danger zone, and by that I mean you're potentially going to overload or overpressure the instrumentation, it will stop. But otherwise it will continue going. And I don't say this to intimidate anyone or make you think that this is a difficult or challenging measurement. It's just, as I think you'll see in a few moments, it's just, you want to be aware of this, because it's going to be important if you want to generate good data moving forward. Also, in the context of wanting to generate high quality data, it's always important also to realize that viscosity is a very sensitive property, which is one of the reasons why it's so useful. It's very sensitive to small formulation changes and also conditions. By conditions, I mean temperature or small shifts, say, in the environment. And with all of this in mind, in terms of how sensitive viscosity is and how the measurements or how the instrument operates, it's always very important that you want to, take a very critical eye towards your data. And in reality, this is just good science anyway. But what I hope people will do moving forward is, when you get your data, you want to look at it and say, does this data make sense? Does it make sense based on, for example, the visual observations I have of the material, of historical data that we have, of data in the literature? How does it, jive with other analytical data that we might have on this type of sample? It's always just a good idea to look at it and see, does it make sense? And as you develop a more basic understanding of rheology and the instrumentation, it's going to be very valuable to you, I believe, because it's really going to help you consistently generate high quality data, which is your goal anyway, and then allow you to properly interpret this data. And then also, if something is going wrong, you're going to be able to more efficiently troubleshoot and take care of the situation. Okay, so let's start at the beginning. So one of the things we wanted to do is get you to understand this calculation that you need to do to get the viscosity, and then also how we choose or design instrumentation to actually implement this process. So let's, a good place to start is always at the beginning. So let's start with rheology in general and what this is. So the common definition of rheology is the science of deformation and flow of material. And this is certainly true. However, a little more descriptive term would be the second line item that I have here, and that is, what is the stress response to a deformation? And I could have an equally valid way of stating this would be, what is the deformation under stress? So the idea is that when we're looking at rheological properties, we're looking at the relationship between stress and some sort of deformation. So we turn towards fluid mechanics. to have a representation of both of these, the stress and the deformation. And so one of these things that we need to describe is this flow field. And where a lot of the points I'm making are going to be specific to viscosity, which is a continuous flow deformation, as opposed to something you would do for just an elastic solid, where it would be a finite instantaneous strain. So we need to address the kinematics, and that's just the terminology that's used to mean the flow field or the deformation. And then we need to address the stress distribution that would be generated upon this deformation. And this is just referred to as the dynamics. So we're going to have the kinematics and the dynamics, which is just the flow field representation, and then the stress distribution representation. And so we need to combine these based on what we know, that we want to look at stress relative to deformation. So we turn then to what's referred to as the rheological constitutive equation. And this is just the big word that's going to give us the relationship between the kinematics and the dynamics, or the stress and flow. So just one quick point while I'm thinking of it. I also, part of this webinar too is to give you the terminology that you might run into if you do want to go look at literature on rheology, or go look at a textbook for reference on rheology. I just wanted to also start putting out there the terminology that's used, so that when you see this, it's clear. Okay, so with that in mind, then we need this constitutive relationship or equation to relate these two things that is relevant to us. And this is actually going to define what the rheological property is. And so what you'll see is that this constitutive relationship is going to define a rheological property, which is going to be specific for a specific type of deformation, and then a specific type of stress response. So basically, different rheological properties are defined based on the type of deformation that you're imposing. As an example of this, which I think many of you may have heard of, and we had about, I guess, a year ago now, a webinar where we were basically focusing solely on differentiating what is steady shear viscosity versus extensional viscosity. And the big difference is really the type of deformation that you're imposing to the system. So you're going to have a different stress response for the different types of deformation. And so that's how the different rheological properties are defined. Okay, so with that in mind, we need to come up with a way of, we're going to have to calculate these properties, stress and deformation, but then we're going to have to measure something to do this calculation. And that's where the instrumentation comes in. So I'm talking about rheometers and viscometers. We personally, our instrumentation only measures viscosity, but we're also going to talk about rheometers in general that can measure other properties as well. So generally what you have to specify here is which item are you going to control. And so you're going to have to control one or the other, stress or deformation. And then that means you're going to have to measure the other. So instrumentation then generally falls into two classes. First off is controlled stress, and that means exactly what you think it means. That means you're going to control the stress and you're going to monitor the deformation. And a large number of the rotational instruments on the market are actually falling into this category. The alternative then is controlled, what is generally referred to as controlled strain, which is the same as controlled deformation. There are some rotational instruments that do fall into this class, and our type of instrumentation falls into this class. So we're controlling the flow through our microfluidic flow channel, and then we're monitoring the pressure drop across the channel, which we then convert to the stress. So we're controlling the deformation and ultimately getting the stress as the output. So they're generally going to fall into one of these two classes. And so also to keep in mind when you're, rheology instrumentation is intentionally designed. And one of the things that's intentional about it is because we know we're going to have to do calculations using fluid mechanics, as we just discussed, you want to make this calculation as easy as possible. So we want to facilitate this calculation. So how is this done? This is done by choosing very simple geometries so that the flow field is well defined and simple as well. And so this is going to be a big factor. So we design them, they're specifically designed to have these very simple, well-defined, well-controlled flow fields, solely for the purpose of making the whole process of the calculation easy. So let's see why that is. Why is it so important to have a simple flow field when it comes to this type of instrumentation? So as we know, one of our components that we need to deal with is the dynamics or the stress distribution that is generated under a particular deformation. And stress is a tensor. And so before anyone gets concerned that this is a complicated topic, it's not. Because everyone, I will argue, is already familiar with the concept of a tensor. Although we'll see in a moment that stress is a second order tensor, I'm sure that everyone is already comfortable with the idea of a first order tensor, which is more commonly referred to as a vector. So vectors, as you know, they have a scalar component which defines the magnitude, but then there also has to be a specification on the directionality. So for velocity, you have a speed, but then you also have to say what direction are you moving in. And for the force, there's a magnitude and also a directionality associated with this force. So it's the same idea, it's just that we need to be a little more specific and we bump it up to the rank of second order. So stress is defined as a force per unit area. So that means we're going to have to say something about the directionality of the force and something about the surface area that this force is acting on, right? So that's why it's going to be this second order tensor. And this is just the notation that we're using here. This is just a common tensor notation. And as stated, we're going to have to specify two things, both the direction of the force and then the surface that the force is acting on. And this surface is characterized by the unit normal vector. So just so you understand this, in case you haven't seen this for a while, what I have here is just basically a material or fluid element in Cartesian coordinates. And we're going to characterize the surfaces as stated with the normal vectors, the unit normal vectors. So that means that the surface that's in the, say, XY plane is characterized by the Z unit normal and the XZ plane by the Y unit normal. And so when we're generating a particular stress, we're going to have to specify what direction the force is acting on the particular surface. So that means there's potentially 9 stress components that can exist if you have an extremely complicated situation. And it's generally written in this matrix type form. And if you want to have a visual of what this is like, I have here basically the different components on each plane. So shear components are going to be, well, let's back up. The diagonal elements are generally what are referred to as normal stresses. And these are the ones that are basically acting perpendicular to the surface. So in this case, T sub ZZ is acting perpendicular to this XY plane characterized by the Z unit normal. Don't get too worried about the notation so much, but just realize the diagonal elements, they're acting perpendicular to a surface. And so when you're doing something like extension or compression, this is going to be a normal type stress. And then also just hydrostatic pressure falls under the class of normal stress as well. Now the off diagonal elements are what we refer to as shear stresses. And this is where we're going to be most interested in and where we're going to try to simplify things as much as possible. So shear stresses now, as we discussed, are basically the motion of the force parallel to the surface. So we have the different potential components of the shear stresses displayed in our graphic here. But now we're just looking at motion of the force that's parallel to the surface. And this is how we're going to basically, this is the result of shearing the fluid. So, okay, so now what's the other parts of the equation that we need basically? So we know we've basically looked into the dynamics and we have a stress tensor, and now we need to think about our deformation. And specifically, we're going to be talking about steady flow, so it's going to be related to a continuous flow field. And then also the constitutive relationship. And we're going to start with this in the tensor form, because what I want to show you ultimately is just sort of a sneak peek of what's coming up, is that, you know, when you choose your geometries properly, everything simplifies dramatically. And that's why it's so important to design these experiments properly, or design the instrumentation properly. Okay, so total stress, which we know could potentially have these 9 components as we looked at the previous slide, is in the full form composed of hydrostatic pressure. So this is just the existence of you know, gravity acting on the fluid, and any sort of containment forces that it has as well. Here, the I is just the identity tensor, so this is just all off diagonal elements are 0 and all diagonal elements are 1. So this is just representing this normal pressure, the hydrostatic pressure. And then we have a stress generated from this imposed external deformation, which we're defining as sigma. So now the constitutive relationship in this full form that is going to define dynamic viscosity, and I'm talking about, and that's what our instrumentation generates, is dynamic viscosity, and that's what rotational instruments, which is probably the most common means of measuring viscosity, generates. So this is the full form of this constitutive relationship, where D is what we're referring to as the deformation tensor. And so just as the stress has 9 potential components, the deformation tensor has 9 potential components. And this looks extremely intimidating, but it won't be shortly. So don't be concerned. And in this deformation tensor, what we have here, U sub I, again, we're looking at Cartesian coordinates just for simplicity, but you could generate one of these for any of the coordinate systems, either cylindrical or spherical. So U sub I is just the fluid velocity in the particular direction. And then we have the partial derivative, or the gradient, in one of the particular directions. So you can see that if we're not controlling our flow field, and it's very complicated, we're going to have a lot of terms to deal with, and how are we going to manage that? That's challenging. So this is where the design of the instrument comes into play. So as I stated before, the flow fields are intentionally chosen to take all of that we just looked at and simplify it down. So some of the common types of shear flows, and I've picked ones that are going to be associated with our instrumentation, and then also the rotational instruments, as those, as stated, are very common. So what we have here are 2 types of flow fields, and I'm distinguishing them as either homogeneous, in this case a drag flow, or inhomogeneous, a pressure-driven flow. And by homogeneous, that term is specific to the shear rate that is across the gap of the fluid. So let's start with the homogeneous drag flow. So what we have is fluid between 2 plates. The bottom plate is stationary here, and the top plate is moving. So the surface is moving and dragging across the fluid. And in both of these diagrams, these red lines, this is how we represent velocity profiles in the fluid as a function of position. So the maximum velocity is at the surface that's moving, and then we have 0 velocity at the stationary plate. So what's homogeneous about this is that, although we have so many equations already, I didn't want to introduce too many more, but what's homogeneous about this is the shear rate across the gap. So because we have a linear velocity profile, shear rate, as we'll see, it's kind of going to fall out of our analysis, but shear rate is the derivative of this velocity. And in this case, the derivative of a linear, of a line is a constant. So the homogeneous descriptor is about the shear rate across the gap. And so this is, for example, what would be a homogeneous drag flow is what you would find in a cone and plate geometry on a rotational instrument, as an example. And we'll talk a little bit about the cone and plate and how that also relates to parallel plates, because it's actually not, parallel plate is not homogeneous, even though it is a drag flow, and we'll describe why later. The other flow, as we're calling inhomogeneous, this is an example of what our instrumentation involves, and this is generally pressure flow in either, say, a capillary tube, or in our case, a microfluidic channel. And in this case, both walls are stationary, and we're applying some driving force. We're forcing the fluid to flow. Since both walls are stationary, now we have zero velocity at both borders or boundaries, and then maximum velocity in the center. And because this velocity profile, again, the derivative is going to give us the shear rate. That'll be more clear later. So we see that the shear rate is not consistent across the gap. So that's the reason for the term inhomogeneous. It relates to the shear rate profile across the gap. And a couple of things to point out with this, both of these flows are still good, however, when you're designing instrumentation, because they satisfy this same requirement that I have here in the center. And that is that we have basically flow in one direction and a gradient in one direction, and that gradient is perpendicular to the direction of flow. And then the other components of the velocity vector are equal to 0. And you'll see why that's important in a moment. But a couple other things to point out about assumptions that are being made, because we talked about that early on, that the assumptions that you make in this whole process of getting the equations is important. And although I kind of hinted at it, I didn't explicitly refer to it as such, but one of the assumptions is that you have no slip boundary conditions. And the no slip condition just means that the fluid adjacent to the plate is moving at that same velocity. So in that case, we have zero motion at this lower stationary plate and maximum velocity equal to the motion of this upper plate. And then likewise here, we have velocity going to 0 at both boundaries. The other thing that's going to be important when you're doing your experiments is that you've achieved a fully developed laminar flow. So 2 points here. One, you're going to have to choose your measurement times such that you actually get this fully developed profile as I've drawn here. So as you would imagine, as you start the flow up, the profile doesn't initially look like this. You would have something that is barely moving near the stationary wall and then starting to move near the surface motion, the wall that's actually moving. And then as momentum is transferred across the gap, then ultimately you do develop this full steady state profile. The laminar part comes in that we want the unidirectional flow where you have the streamlines that aren't crossing each other. So very much is represented by our drawing of velocity profile. So when you get to high enough rates in certain types of instrumentation, depending on the characteristic length scale, and that characteristic length scale is generally going to be the gap between the plates or the fluid height, you can see this transition from this laminar flow to what's referred to as turbulent. And turbulent, if you're not familiar with it, has what is called secondary flows, is another way of calling it, but it will basically have, instead of these nice streamlines that we've drawn here, they'll have things such as eddy currents that actually add an artificial resistance to the flow. And so those will show artifacts in the data if you go to the onset of these secondary flows that exist. And the other thing that's important when this is happening, and I don't want you to get confused with my terms here, but I couldn't come up with another word to describe the fluid other than homogeneous. But you do want your fluid to be on the length scale of the instrumentation to be homogeneous. So it should be macroscopically homogeneous. So you don't want gross phase separation so that you could have different layers of fluid slipping past each other, is what I mean. So we're talking about homogeneity with respect to the flow field, more specifically the shear rate profile across the gap, but then also the nature of the fluid is important as well. Okay, so these are common flow fields. One of them is what we have in our instrumentation. One of them is in a very common rotational geometry. So now what we can do is we want to take that more complicated tensor relationship for the constitutive equation and simplify it down. So first thing we can do then to get there is to simplify this deformation tensor. And how are we going to do this? Uh-oh. Okay, sorry, my animation was off. I apologize. Okay, I intended to do that step by step, but here it all is. So we want to simplify the deformation tensor. And so if we remember, based on our two types of flow fields, because we're going to simplify in the same way for both of those, remember in the Cartesian coordinate system, we've generated flow fields where we have only one component of the velocity, and it's only dependent on one variable. And so that allows us to take this very large, intimidating deformation tensor and basically strike out everything that I have here with the red arrows. So that simplifies everything down so that we only have two diagonal terms now, which are equivalent. They're implying that this tensor is symmetric, and it's related to this velocity gradient perpendicular to the flow direction. And so then we can substitute this into our constitutive equation, getting again two components of the stress. And this is the point where it's appropriate to define the shear rate, although we've sort of alluded to it earlier, as this gradient in the velocity perpendicular to the flow. So you always think of shear viscosity as basically forcing these adjacent elements to move past each other. And this is what introduces that type of motion. So now the final line here is basically giving you the equation that you're used to seeing in scalar form. And this, of course, is open to the possibility that the viscosity is going to be non-Newtonian. And in case you're not familiar with that, Newtonian viscosity is one that is independent of shear rate, and non-Newtonian is one that will vary with shear rate. So the resistance to the flow will vary with the flow field, essentially. And of course, you can have a dependence on temperature as well. Okay, so that's the expression that everyone is most familiar with, and it's you get there and can apply it when you are using one of these pieces of instrumentation that is controlling the flow field in this manner, in a well-controlled simple field. So ultimately, in the talk today, we're going to go through how are these things, the stress and the shear rate, calculated for some of the different types of instrumentation. But before we get there, I want to first contrast one of the other common types of instruments. So we focus a lot on the idea that using a simple flow field is very advantageous, but there are instruments that don't use these, and they have what we'll call a complex flow field, and oftentimes these are referred to. They'll generate what is referred to as a viscosity index, and so the instrument is often called a viscosity indexer. And here's just a visual example of one option for this, and I've drawn it as a rotating disc or rotating spindle in a fairly large volume of fluid. Now, of course, these types of instruments, because they're used for quality control in a variety of industries with a very broad range of samples, you can buy these particular spindles in many sizes and then also different geometries. So I drew the disc, but you can find something that looks more like a cylinder. You can have a vane. There's many options for this, depending on the industry and the samples that you work with in that industry. But one thing you'll notice is that I didn't draw a well-defined flow field or velocity profile as I did in the other geometries, because that's difficult to do in this situation. But there's one thing I think that is clear, and that is that now we're looking at cylindrical coordinates to characterize our components of the velocity. What I think would be clear, though, is that as we rotate this spindle with some angular velocity, the predominant component is going to be in the theta direction or the angular direction, and it's going to depend on both the radial position and then also the height of the fluid in the container. So now we can't define a single shear rate like we can in the simple geometries that we just discussed. So these types of instruments are perfectly useful when you're dealing with quality control type applications. So if you want to make the sample behave in the same way every time. So for example, you're formulating and you want this product to behave the same every single time. If you test with the same spindle and then also at the same rotational rate every time, you'll see whether or not things are changing. It's harder to interpret in a theoretical sense. However, it's still perfectly useful to monitor things in a quality control environment. It does become challenging, though, if you want to start comparing data from this type of instrument for non-Newtonian samples on instruments that we've just discussed, where you do have a well-controlled shear rate. So this is where it can get tricky when you start wanting to compare, and this is one of the comments we got in the signups, is that they have trouble when they start comparing viscosity data from one instrument to the other. And this is a situation where it can start to become a problem because you have a well-defined shear rate in one case and not in the other. So you're getting viscosity as a function of rotational rate and viscosity as a function of shear rate from the two different instruments. So this is can be a bit of a challenge if you want to make the comparison. So that's really all I'm going to say at the moment about the complex flows. I just wanted to put it out there because it is a measurement, and this is one of the, since we're talking about the flow fields, the kinematics, I thought it would be, and these are also common, particularly in the quality control. I wanted to make the contrast with those and point out that if you are having challenges making comparisons between this instrument and what I'll call a more research level instrument, then this is likely the problem. Okay, so I wanted to then, so we know we've simplified our constitutive relationship down, and we're going to have to look and see how from our instrumentation are we going to calculate shear rate and shear stress. So I'm going to spend a little more time on our instrumentation because we're most familiar with that, but then I will also talk later about the calculations that are used for a couple of different geometries on the rotational side. So I'm not sure how many of the people attending are familiar with our instrumentation or not, but we're quite different than the rotational type. And what we have is basically, I should have defined it here, but our technology's name is shortened as VROC. So it's viscometer, rheometer on a chip. And so what we have is a microfluidic flow channel, and we're forcing fluid to flow through this channel. Here's a cartoon of our flow channel. And where beneath the flow channel are 4 pressure sensors. And this is sort of a more realistic diagram down here in the corner of the bottom side. So if I took this flow channel on the top and flipped it over, now you can see the presence of these pressure sensors that are beneath our flow channel. And I just wanted to go into detail so you could see how all instrumentation is going through some multi-step process. I'm not going to give all the steps in the other instruments because, as I said, I'm not as familiar with those as I am ours. But there's going to be some, analogous process. So when we talk about this more generally, we're talking about how we're ultimately going to take this pressure drop here. This pressure drop is a function of sensor position, and use this to calculate the stress, which we do. But in reality, there's a step prior to that, and that is actually we're first initially getting capacitance. So as the fluid flows through this flow channel, these pressure sensors are going to deflect by some particular amount. And on the opposite side of these sensors will be some counter surface. And as they deflect a different amount, depending on the pressure that is in the flow channel, we're going to have a different capacitance value. So D is just the difference here, and A is the surface area. And then these are the dielectric constants of the material, and then also the free space between the two surfaces. And so, when we calibrate, and our instrumentation is calibrated in-house, so there's no calibration that's done on site, you would, consistently check standard materials to make sure everything's performing okay, but you're not ever going to do a calibration that's done in-house. So we're calibrating the capacitance, I guess, the pressure in the cell. And then we use this capacitance then to get our pressure drop across the flow channel. So this is sort of the first step in the process for our instrumentation. And then sort of putting it all together is now we want to take that pressure drop and get our viscosity. So our instrumentation, as I mentioned earlier, is a controlled it's a controlled strain instrument. And so what we're controlling is volumetric flow rate. And so we're controlling the amount of fluid that flows through this flow channel. And the first step of the calculation then is, because our system is what is considered one of these non-homogeneous flow fields, and the exact velocity profile we won't know until we determine whether or not our fluid is Newtonian or not. We start off with assuming the Newtonian assumption, which allows us to calculate what the Newtonian shear rate would be at the wall as a function of this volumetric flow rate, and then the dimensions of the flow channel, just width and height. And then similarly, now that we've gotten our pressure drop across the flow channel, which we've represented here, and as stated, we do know well the geometry is well characterized, so we know the dimensions of the geometry. We can calculate the shear stress. And from that, we can calculate what we refer to as an apparent dynamic viscosity. And this viscosity is correct if your fluid is Newtonian. However, because it's this non-homogeneous type of flow field, and you have a variation in the shear rate across the gap, if you find out upon doing a rate sweep that your sample is non-Newtonian, then we're going to need to make a correction for the shear rate value. And one of the comments that came in with the signups is, when do you need to apply certain types of corrections in the capillary flows? And so this is a situation where you're going to need to apply one of these corrections, and that would be the one for the non-Newtonian sample, the very long name Weissenberg-Rabinowitsch-Mooney equation, shortened for WRM. So in this instance, what you would do is you would stress is fine. Stress comes just from this pressure drop, and we don't need to correct it. There's no need here. However, we made an assumption when we calculated our shear rate, and so this is going to require correction. And so what we can find is that we can use our data that we got at multiple rates, and also the Newtonian assumption value for the shear rate, and then calculate the true shear rate. So what we would do is we need to get from our data this quantity here. The derivative of log of the shear rate versus the derivative log of the stress. And you can find a derivation for this particular correction in a number of rheology textbooks. I didn't want to go through it, but if you're interested in math and want to see where it comes from, that's documented elsewhere. But here is an example of some data where we're doing the correction. So you can see the original blue data is uncorrected. And then we look at this shear rate that we've calculated, the Newtonian estimate or approximation versus the shear stress log scale. And one thing to also point out is you never need to correct anything that looks like it's on a Newtonian plateau. So we have a little noise here, but on average, it's not yet shear thinning. So we really only correct data in the shear thinning region. So once we get the true shear rate from this fit to our data, or a modified version of our data, then we can go back to our scalar constitutive relationship and calculate the true viscosity. And this just shows you the extent to which things typically change when you make this correction. So if you're very concerned about, getting, accurate results, then you should absolutely certainly do the correction. But you can see it's not a massive change if, certain level of accuracy is not that necessary for you. Okay, so one of the other things I wanted to mention with respect to our channels and things that you might want to consider, we had mentioned that there's two things when you're dealing with the microfluidics or the rectangular slit geometry, which is different than when you're dealing with the rotational geometries. So, Reynolds number is still important in your other geometries, but it seems to because of the length scales that are associated with those, you tend to have more issues with turbulence in those geometries. So I wanted to point out that, if you're concerned about predicting whether or not you'll have turbulence in our microfluidic geometries, you can look towards the Reynolds number equations, which is just looking at basically inertial to viscous forces. So when Reynolds number is small and viscous forces are dominating, then the onset of the turbulence or the onset of secondary flows isn't going to occur. But then once the Reynolds number gets larger and larger, which is going to come from a ramp up in, say, volumetric flow rate, then you can see this transition. And this transition generally can occur. The value varies a bit, but somewhere around 2300, 2500, something like that is where you go from laminar to the turbulent, where you have secondary flows or eddy currents. And so the only thing we need to know to calculate this Reynolds number are our volumetric flow rate, the density of the fluid we're looking at, the estimate of the viscosity that we have, so we could use the Newtonian low shear plateau, for example, or anywhere along the shear rate curve, and then also the dimensions of the flow channel. And what we can see is that when we're dealing with something, we have an example of how this parameter plays out and whether or not we would expect turbulence in our flow channel. So this is just for water at 25 C, so that's slightly less than a centipoise. And we're using basically our highest pressure chip, so the chip that we can, highest pressure and smallest length scale channel depth, so we can get to the max flow rate. And so even if we were to use this at, say, a shear rate of over 2 million, Reynolds number is still quite small with respect to the onset of these secondary flows, which can be problematic and sort of violate the assumptions that were made when we're setting up the calculations. Another difference between our instrumentation and the rotational instruments is that our fluid is entering and exiting this microfluidic flow channel, whereas when you have the rotational geometries, that's not the case. Your fluid is basically always in that geometry, just being sheared. So one of the things you also need to consider in ours is confirming that you don't have to do the additional correction, the Bagley correction, which is going to account for entry or exit effects. So in our case, the way the pressure sensors are set up, they're specifically set up to be far enough away from entry and exit that the true pressure drop that we get across the flow channel doesn't really need to be corrected due to any disturbance from entry or exit effects. And so you can sort of estimate this. There are different equations you can find in the literature. This is an example of one of them, where you want to estimate how long is it going to take after the fluid enters the channel to no longer be impacted by that entry effect. And again, it's going to depend on what we refer to as the hydraulic diameter of the flow channel, and then also the Reynolds number. Hydraulic diameter is just defined as this for a rectangular geometry, just relating to the height and the width. And so what we see for this particular water example is that the entry length is going to be about 0.75 millimeters. And I've pointed out here that our first pressure sensor isn't positioned until slightly more than 2 millimeters past the entry. So in our case, for this particular material, at these high flow rates, we don't need to worry about any sort of correction for entry and exit effects. Okay, so with that in mind then, let's move on to some of the calculations for rotational instruments and see how they are going to differ with respect to the VROC technology, or microfluidics. So here are two examples, and I've picked two. These are very common, and they represent both what we've talked about before, an inhomogeneous flow and a homogeneous flow. So let's start with the simplest one first, which is the cone and plate geometry. And this one is actually specifically designed so that you do have a homogeneous flow. So the shear rate, which you can again derive yourself from the fluid mechanics, or you can look it up in a Rheology textbook, is just going to be related to the rotational rate of the upper tool and the angle between the cone and the lower plate. And so what you'll see is that, so if you remember, the general rule here for the shear rate is going to be the linear velocity divided by the gap. And so what we'll see then is that as the linear velocity, which is going to decrease as we move inward, because it's going to be proportional to r, is going to decrease in proportion with the gap height. That's the nature of the cone geometry. So this gives us a uniform shear rate across the radius of the tool, and can then therefore be referred to as homogeneous. And so the stress then is just going to come from the geometry of the tool, so the radius of the tool, and then the torque that is required to achieve this particular rate. And there's no correction needed here because it is what we refer to as a homogeneous flow. However, the parallel plate geometry, because it has one gap across the entire radius, is in fact a inhomogeneous flow. Even though it's the basically drag flow that we talked about earlier, it's still not going to be homogeneous, because if you look at the shear rate, and this is my explanation for the linear velocity divided by gap is a little more clear here. So the numerator is the linear velocity, which is maximum at the edge where the distance is equal to the tool radius, and then goes to 0 as we move towards the center. However, the gap is constant. So shear rate is maximum at the edge and then goes to 0 towards the center. So that means if you have a Newtonian fluid, we can define something analogous to our apparent values, and that being an apparent stress, where now if it is Newtonian, then this is perfectly valid. And again, we're just using the tool geometry, the radius of the tools, and the torque that is required to rotate at some particular angular velocity. However, if it's non-Newtonian, it needs a correction similar in form to what we use in our microfluidic flow channel, but specific to this. So again, you're going to need to look at, you would need to get, both in this case, and if you need to correct data for our flow channel, you need to get values at multiple shear rates. We recommend at least 3, better to have more though. So, you know, I point this out because, as I stated before, there seem to be some misconceptions about, you know, when you compare different instrumentation with each other. And this is where, you know, all instruments are doing the calculation. No one directly controls shear rate. Shear rate, for example, is always calculated. You're really controlling, you know, angular displacement, and then using the tool geometry and your gap fluid height to calculate the shear rate. And then from the torque and again the geometry of the tool, you're calculating shear stress. So everything is calculated, generally this multi-step process. And you know, so you can't really, you know, this is where they're all the instrumentation is sort of on equal footing, is that this is a calculated property. Okay, so I can make a good, so I want to kind of start, you know, since these some of the questions that came in with the submissions for and signups for the webinar were, you know, directly related to our topic today. So I wanted to fit some of those in there. So one of these was on how do you make the decision on what tools to choose depending on your sample. So I can make a quick comment when it comes to choosing flow channels for our instrumentation. So we had talked about the pressure sensors that are beneath the flow channel, and we make flow channels with different pressure sensors with different sensitivities. So they're meant to operate in different pressure ranges. So you would use a flow channel specific, you know, choosing that pressure range that you needed for your particular fluid. And then also you can adjust, we have different channel depth, which is going to, you know, be relevant depending on also the viscosity that you want to test, but then also the shear rate that you want to achieve. But in general, it's always the same geometry. We're just changing depth and changing the sensitivity of the pressure sensors. It's a little different when you're looking at changing tools for rotational instruments. So what's the general rule of thumb with this is that you want to, because what's really going to matter in terms of looking at the different viscosities is, are you in basically the acceptable torque range for your instrument? And so one thing that's going to impact that is the surface area that your fluid is in contact with. So what you would generally do is move from left to right as you decrease your sample viscosity. So high viscosity materials you would use with small, either parallel plates that I've drawn here or small radii cone and plate geometries. And then as your viscosity decreases, you would want to then increase the size or dimensions of your tool. So that could be either choosing a larger diameter parallel plate or cone and plate, or ultimately that could mean moving to what we refer to as a couette or a cup and bob. But the general thing is that as you decrease viscosity, you want to choose a tool that's going to have an increased surface area, which is going to increase your torque, and then make sure that you're able to do measurements within the lower torque spec. So while we're thinking about, one of the comments that I made at the beginning is that you always want to be mindful of how you're doing your experiment and think about all of the things that need to be, conditions that need to be met. And this is very important and relevant to some of the comments that we got during the signups, and that is, the idea of getting inconsistent data, and not just, with an individual person, but then also inconsistent data from person to person, and instrument to instrument, lab to lab, things of that sort. So some of the things that you can keep in mind when you're, trying to, improve your measurements is, one important thing in terms of the rotational tools is the fill volume. So you can imagine if the contact area, the calculation is assuming that the instrument is filled to the very edge. So if people are loading these tools differently, some, overflowing the tool, some not quite filling it enough, this is going to give variability in the value that you get, because the calculation is assuming that the fluid is making full contact with the plates, and no more, no less. So it's made that assumption, and if you're violating it, then you can see differences. The other thing, which we mentioned before, is steady state. You want to make sure that you choose timing on your experiments so that you get a fully developed steady state velocity profile. Because as we mentioned, and this is more important as you go at lower angular velocities, because it's going to take longer then to reach that steady state value. You want to make sure you're operating in sort of the bounds of the instrument. So it's easy not to overload or over torque, because the instrument will stop you, because it doesn't want to damage. But it's easy. It's a little more challenging to make sure that you're working above the minimum torque, and then also above the minimum angular resolution, because it's still going to do the experiment. Generally you'll get some indication in the software, but if you're not paying attention, you might use this data that's below the torque, minimum torque, or below the minimum angular resolution. And by angular resolution, I just mean the tool needs to know that it's moved or displaced a certain angle. It has to move a certain distance before it knows that it's moved. Also, another important point is the environment, controlling the environment. So one of these, of course, is evaporation. That's a common one. But you can also have samples that are sensitive to humidity and actually pick up water. So hygroscopic samples can actually change during the test if you're in a humid environment and you're not controlling for that. We've talked about the homogeneity of the sample before. You don't want any macroscopic phase separation, or you're going to disrupt the flow field that you're assuming that you have for the calculation. Wall slip is another potential issue. This, of course, is more related to very high molecular weight polymers like millions, or large length scale, say aggregates of colloidal particles. As soon as you start getting into larger length scales of the objects you have in your solution, then you can start to get concerned about wall slip. We could do a whole discussion on wall slip and how to detect it and how to handle it. So I don't want to go into it too much there, but you want to think about that. If your samples fall into that category of very high molecular weight or larger length scale aggregate structures, network structures, then you want to dive into that as a possibility. We've talked about turbulence causing artifacts. Once you go to very high rates in these types of instruments, you can have sample loss, or depending on the exact nature of your sample, you can have edge fracture. And then also the gap distance. Some people try to operate at very narrow gaps to bump up the shear rate that they can achieve, but that can be difficult because there's a specification on how parallel the tools are. And so if you're operating in the gap that's acceptable, then this off parallel nature won't be a problem. But as you narrow gap more and more, then this can be an influence on the measurement. So those are just some thoughts, keep these in mind. Some of these you may know are not a problem for you, and so don't worry about them. But it just, be aware. So I feel that I've went on a little too long. My intent was to go over some questions that came in with the comments, as we waited for other questions to come in. But I think what I'll do before I do that, we'll see how many people are still with me, and if there's any questions that have come in specific to today's webinar. So let me see. Okay, so it looks like we have questions. So let's look at the present moment questions before we do two other ones. Okay, so first question that we have is, do we need to do any sort of correction for thixotropic fluids? So in case you're not familiar, so obviously the person asking the question understands, but just for the general audience, thixotropy is really a time dependence in terms of restructuring of a fluid. So, one misconception that exists is that thixotropy is equivalent to shear thinning, and that's not quite true. So thixotropic materials will shear thin, but there's more to the story in that case. So what happens is if you have a thixotropic material and you're ramping up your shear rate so that you see and introduce the shear thinning, and then if you went immediately back without waiting any time to that low shear rate, you would actually get a different viscosity value. Because what has happened is that shear process has broken down the structure, and the time scale of restructuring is long compared to your experimental time scales. So that's the nature of thixotropy. And in terms of any sort of correction, you would need to correct for the shear thinning aspect of it, but that would be all. So you would have to, so if you're using a tool that has the non-homogeneous flow, you'd need to correct for the shear thinning part of it. But in terms of the time dependence, that's, that's still okay. So then also, do we need to adjust for suspensions and emulsions with multiple particle sizes? Okay, so when you're talking about multiple particle sizes, the only thing you need to worry about there, so presuming, so the issue with particle size is not so much as if it's polydisperse, but what is the size of these particles relative to the characteristic dimensions of your geometry. So you want the particles, max particles, to be at least no more than 1/10 of the length scale. So that would be either the channel depth in our instrumentation or say the gap that you have in one of the rotational instruments. So the issue with particles is really the size relative to the dimensions in the rheometer, in the tool geometry. But other than that, you don't need to make any adjustments. You need to just choose the appropriate tool. Okay. Okay, so how can we determine the yield stress using a capillary rheometer? So that is a little more tricky. So, I'll be quite frank, if you can use the capillary rheometer to look at this. So generally what tends to happen when you're dealing with a yield stress fluid. So we didn't define that property in our discussion today. So let me first, before I get into the question, make the general comment for everyone listening. So the yield stress is basically if you have something, you have a fluid, so it will ultimately flow, but it's able to support a particular stress. So it's almost like a solid until it's, you pass that tipping point basically, and you pass the yield stress, and then the material structure starts to break down and actually becomes a flowing fluid. So it's sort of solid-like at rest, and then once you go beyond its yield stress, then it will flow. So if you remember at the very beginning, we talked about the two types of rheometers, the controlled stress versus the controlled strain. So really controlled stress instruments are better when dealing with yield stress materials. You can use the alternative, the controlled strain, and you can use capillary rheometers. It's just a little more tricky, I think, because what tends to happen is that you tend to have this transition where you're going from something that's starting to break down near the wall, and then this breakdown length scale basically propagates and spreads across the gap. And so you can look for some signatures in both the transient curve and then when you plot stress versus shear rate. So in the transient curve, oftentimes when you're having a yielding material, you have an overshoot, so you can use that to sort of identify it, and you would see that. We've seen that in our capillary instrumentation. And then also you'd want to look for basically if you looked at shear stress versus shear rate to see if you could extrapolate to a non-zero value at shear rate going to 0. So you can deal with it. It's just not the ideal type of instrument for it, I would say. Someone's asking what textbook is good for background in rheology. So I would recommend McCosco's book is very good. That's probably my favorite. He's at I think he's retired now, but Chris McCosco was at the University of Minnesota. I don't remember the exact title of the book, but it's maybe Concepts or Principles of Rheology. But if you search his name, Chris McCosco from University of Minnesota, I'm sure you'll find the text. And that's a very good one. I like that one. So let's see. So someone's asking about a future webinar on wall slip, and yes, we can definitely do that, because so what we didn't get to mention are that we started to present. As I said, when I made the title, I overstepped my bounds, and we can't cover everything. So I kind of feel kind of bad because I said look out for all these problems, but then I didn't tell you how to handle them, because you can identify whether you have wall slip, and you can do this depending on the instrument you have. The main thing is you want to adjust either gap if you're doing rotational, or in our case channel depth, and basically the slip velocity or slip length will change with the channel depth. So we can address wall slip in the future. That's certainly something there. Let's see. Okay, so someone's asking about which types of industries VROC, which is our microfluidic viscometer, is most useful for, and is it only used when dealing with non-Newtonian flows? So the answer is we actually have VROC's instrumentation across the board in a whole variety of industries. It is very common in pharmaceuticals, mainly because of the low volume requirement. And so anytime you need low volume, it's a good option, whether that's because you just don't have much or it's very pricey and you don't want to use it. But it's very common in pharmaceuticals. But in reality, we have it in every industry, from personal care to paints and coatings, oil industry. The only times it gets challenging is if you have materials with a very high yield stress that can be difficult to clean out. But and even then you can, if you really prefer it, you can, we have app notes for specific industries where you can actually displace those hard to clean fluids. And it's, you can use it for Newtonian or non-Newtonian. It works either way. So if it's Newtonian, then you just get the data and you have no concerns about the correction. If it's non-Newtonian, then you apply the correction, which is straightforward. And then there's a question about our channels. Are they disposable? And the answer is no. The channels are designed to be used repeatedly, and generally, with our customers, when they purchase them, we will talk to you and try to guide you in coming up with the best cleaning protocol for the type of samples that you have. So meant to be used again, not disposable, definitely can clean them. And we're happy to, work with you and share our experience that we've had internally and with our other customers to help you develop a cleaning protocol to make sure everything is okay. And actually I won't guarantee this length of life, if you would purchase our product, but I think we have some flow channels that have been very well maintained and are still around from, 2010 timeframe, somewhere around there. So definitely they, when maintained, can last quite a long time. So a comment was made that biopharma is really the only field that they think that this technique could work in. And it certainly does work in biopharma. People working with proteins and antibodies do prefer it for small sample volume, and then also the ability to get to very high shear rates that are consistent with injection rates. But as I said, it's popular in all the other industries as well, everything from the personal care to oil, paints, coatings. like I said, as long as it's a fluid and it flows, even if it does have a modest yield stress, it's something that can be handled in the microfluidic channel. Okay, this is great, all the questions. So if the material has two shear thinning regions separated by shear thickening, should we follow the same correction procedure you presented here? So in that case, so I haven't personally seen the material in our instrument, tested in our instrument that behaved in this manner. So what I think would happen is, if it's an instability, you know, my first thought is maybe you could correct, if you felt the shear thinning regions were stable, well-controlled flows, then certainly applying the correction there is absolutely valid. You could apply a separate, you could break it up in pieces and apply the correction to the different regimes. Although if you're indicating that it's thickening because it's unstable, as you know, perhaps you know, secondary flows or something, I'm not sure what you mean by that, then I'm not sure that you'd want to go to the trouble of correcting it if it's an unstable flow to begin with. But you know, in all honesty, I don't have experience with that, and I'd it's kind of my off the top of my head answer. But let me think about that. And maybe if you want to contact us and tell us a little bit more about that, you know, we'd be happy to learn. If you could share, you know, in general terms, the type of samples you're dealing with, and a little more detail why you see that. So what do we have? A few more. They're asking about the sample volume in the microfluidics. So that sample volume required for the testing is going to depend on the instrument that you have. I was really focusing on the technology in general, not our different styles of instruments, but it could be anywhere from, the flow channel itself is roughly, you know, filled with a microliter or so. But because you need to make sure you're flowing enough volume through to get repeat measurements, and then also make sure you're getting to steady state and doing an average over a long enough time, you would need anywhere from 26 to maybe 50 or so microliters for an experiment, because you're just going to need to pump the fluid through the channel to get multiple data points and be able to get to steady state and average. But yes, the flow channel itself is in the vicinity of a microliter to fill it. However, if you're, you know, concerned about volume and wasting volume, one of our instruments has what we refer to as sample recovery, and you can actually get your sample back after the testing, or at least a portion of the sample back. Of course, the sample will wet internal components of the instrument, but you can get a big portion of it back. So minimum torque for method development on viscosity. So minimum torque requirement, so our particular instrumentation has a minimum pressure, so we don't deal with torque. So really the minimum torque is going to be a spec that comes from the rotational instrument. And then the viscosity that you get at that minimum torque is going to then also depend on the tool that you're using. So yeah, I can't answer more than that. The minimum torque is really going to be a specification that comes from the rotational instrument. And then the data you can get with that will also further depend on the tool that you choose. Okay, so there's a question about using our system with high viscosity polymers, and the example is nylon. And if our instrument is not useful for this, could we recommend another type of instrumentation? So we've measured nylon in solution, so in organic solvents. So we had a customer who was interested in nylon in formic acid. And so solutions of nylon are okay in our system. But if you mean melt rheology, where you're looking at neat polymers, then that's not necessarily going to be the best. We're not going to be the best option for you. Even our high temperature system generally isn't going to go high enough to get above transition temperatures for both melting and glass transition. So, you know, we've definitely done nylon in solution, as I said, formic acid, but in terms of something like a neat polymer where you want to do melt state, then it's probably not the best. So another question about size volume size. I think we covered that. Okay, so there's a question about, I had mentioned the sample should be homogeneous, and then there's the comment that, well, what if you have something that, I believe what they're indicating is that they have something that's aggregating. So they have, they're talking about proteins specifically, or antibodies. And so as you know, proteins and antibodies are what I would call metastable, meaning that ultimately over time and depending on the conditions, they'll start to aggregate and form dimers, trimers, and then even aggregates with a larger number of proteins in them. So what you end up with is this polydisperse distribution of, say, aggregate sizes of these proteins or antibodies. And that's not necessarily going to be a problem. So what you really want to think about is so if everything is homogeneous if you zoom in to small enough length scale. So what you want to think about is, what is the length scale of that in homogeneity, and how does it compare to the tool geometry? And what you want then is this, length scale of inhomogeneity with the sample to be small compared to the length scale of the tool. So in our case, that's going to be the channel depth. So if you're working with, one of our common channel depth, which is about 50 microns, you need to believe that the aggregate structure is significantly smaller than that. And since proteins themselves, the primary unit is generally somewhere around, let's just say, 5-6 nanometers or so. Even if you have many proteins in an aggregate, it's likely going to be okay for that. So that's how I would approach analyzing that. Now, if you're having one of the other things you can have is liquid-liquid phase separation. So if you start seeing that and it's visible, then that's a problem. So that's another thing that can happen based on the fact that you have attractions in the proteins that can lead to these liquid-liquid phase transitions. If that's on the macroscopic scale, then that could be a problem. So then there's a general question asking about performing method validation and method development. So that's very specific to the types of samples that you're dealing with. So when you want to specify the method that you want to use and validate, it's really going to be dependent on, you want to ask yourself some questions to get to that point. So obviously you know what samples you're working with, and so what you really need to understand is what you're trying to learn about these samples. Are you measuring viscosity because you want to predict performance, or viscosity is a great tool as an investigative tool to understand how components are interacting. So then if that's of interest to you, then you need to think about that. So you really want to ask yourself, given the samples that I have, what am I trying to achieve? Is it predicting performance, or is it understanding sample components and interactions so that I can better formulate, or is it both? And then you'd want to start setting up the experiments, whether you need to do rate sweeps for that. So if you need to get to a particular rate that corresponds to your application, so then you'd want to start thinking about trying to estimate a shear rate that's relevant to your application process. So I don't know what industry you're in, but for example, as I said, pharmaceutical companies are big customers of ours, and they're often interested in shear rates that occur during injection or filtration even maybe. So you'd want to start looking at what rates are realistic for that particular application, or whatever application it is. And then, if you're looking at trying to understand component interactions, you may want to do that in a concentrated state and look for shear thinning, or you may want to do it in a dilute state and look for intrinsic viscosity. It's really very, you really want to, it's very specific to your samples and what you're trying to learn. So if you want to contact us and share a little more information about your samples and how you want to apply viscosity, we can certainly talk to you about that. But that's sort of what you want to start, that's the thought process I would start suggesting that you go through to start to identify the tests you want to do. Yeah. Okay. So I think I got all the questions submitted today, and because I went so long and we had such a great number of questions come in today, I will stop there, and in future webinars we will address more of the questions that we had that came in with the registration comments. So thank you so much for all the questions. That was great. I really it's very helpful to us, and then to all the other viewers. So with that, thank you so much for attending. We really do appreciate your support, and I wish everyone well out there. And please join us again at our next activity or event. Thanks a lot. Have a good day.